I wasn't exactly sure who was going to be in the audience, but it's all right. So I can actually just skip over all of that. Anyway, these are just updates. I won't be stepping necessarily through each package. These are more sort of samples of work that various developers have been doing or applications. And so I alluded to this yesterday. There's been some work in AMG, in MULU specifically, for a new strength of connection. And this is just a reminder, which is going to lead into the next slide, that multi-grid is, it's basically you've got a fine grid problem, and you're solving a residual equation on these coarse grid systems. And as opposed to geometric multi-grid and algebraic multi-grid, it's the job of the AMG to develop the grid transfers, right? It gets the linear system and then builds up the coarse grid systems. And so a lot of the magic is in the secret sauce is, well, how do you build these grid transfers? And so Christian and Chris and Malachi and others have been working on a new strength of connection. So, the classic multi-grid, you sort of are looking at the individual matrix entries, and you're doing some sort of equilibration. You're deciding, oh, for a given degree of freedom, I'm connected to this other degree of freedom. Is that a strong or a weak connection? And so in the classic sense, you're just sort of comparing the two entries, with some equilibration due to, with diagonal entries. There's an alternative, which is to build essentially what we call a distance Laplacian, which is based purely on mesh coordinates. And so those are the two classic pieces that we've had for a long time inside of MULU. And so this LDRD, led by Chris, has been incorporating those two. It has been incorporating both the idea of a mesh stretching, so to detect grid anisotropy, but it's also incorporating a new material parameter. This, wherever it is it? No, the sigma. Thank you. It's the sigma, right? And so this is something extra that the application would pass in, but this is typically something that the application does have at hand. And so they've been sort of developing this, and they actually have a pretty nice demonstration based on this thermal battery. And here's a sort of a cartoon image. I'm not going to walk through all the details of the thermal battery because I don't know the details, but Malachi is the expert and can tell you about it. But basically, there's this comparison here where, they're sort of changing this theta, this dropping factor, and then comparing, well, how many iterations does this take? And the key takeaway here is in the classic, this is something that the user has to tune. And in the classic case, you can, in the classic case, you see these iteration counts, actually iteration counts over there, and this is, I think, iterations times multi-grid complexity. And you can see for the classic case, well, things don't work super well. And then I think for the, let's see, for the distance Laplacian, it is working a little bit better there, but there's still some sensitivity as you dial the theta. And then when you incorporate actually the material properties, you have a much broader range for that theta, and that's the key. There's less sensitivity there. There's often, that's one of the things when people say, well, I'm not seeing good convergence, what do I do? Oh, well, have you tried changing your dropping threshold? Well, what's a good threshold? I think often we say like 0.02 or something. All right, so that's a very nice result.
Okay, just interrupt.
Yep.
So is the intention here that then you would, instead of just passing in your matrix, you then pass your matrix and your diffusion coefficients? Is that all it is?
Yeah.
Okay.
Yeah.
And coordinates, yeah.
Yeah. But we often, we always ask for coordinates. Yeah, we use them for multiple things, right? So this is an additional thing. And I think the idea is that this material property should be something that the application has sitting around anyway. All right. So then I wanted to jump to direct solvers. This is actually so Shilu Basker is the direct solver package that I talked about yesterday. And this is work led by Ichi Yamazaki and then Clark Dorman, who recently retired, and then Andrew Higgins as well. And this is the impact of work in Shilu on the Zeiss circuit simulation application. Heidi will actually be talking about this later today. So these the takeaway here is that Zeiss has very, very difficult linear solvers, or linear systems to solve. I guess, there may be some cases where you could do an iterative solver and it will converge. Maybe. Oh, okay. No. So typically, they go to a direct solver. And the classic one to use is KLU, the Clark Kent LU, developed by Tim Davis. That it relies on this block triangular form. And of course, the challenge for modern circuit simulations, they don't have this BTF structure. They're dominated by this large diagonal block. And so Ichi and Clark and Andrew have improved the solver performance for the diagonal block inside of KLU. And so the impact here is due to their work, they've seen about a 4x, Zeiss has seen about a 4x improvement in overall simulation time. And so this graph here sort of shows the impact over the original one. There was an intermediate optimization, and then this is the Shilu Basker line. It looks like they're working on they're continuing to look at distributed memory sparse direct solver. Yep.
I'll just ask, is that new matrix scatter in KLU2, like anyone who's using the Mesos 2 KLU2 will also get that minor benefit?
That's a great question, and I don't know. Heidi, do you know?
I think they did put it in more generally to be anything, because we also use direct solvers, just not through this, but outside of it, and I believe it applies to any use that we're asking out.
Right. And are you thinking specifically for KLU2?
Yeah.
Or yeah.
I think it's actually within the framework. There's usually a process that moves everything in one processor.
Right.
If it's a serial solve, and I think it applies to any of the solvers that Mesos 2 that actually require that.
Like KLU2.
Yeah, like
Yeah.
for example.
Yeah. All right, so next, so Alexander and Alexander Heinlein sent me some updates for Frosh. So it's being used in FeetFlow, which is an incompressible 2D and 3D simulation code. And so this is a Stokes problem here that they're solving. And I think that the main takeaway here is that they're seeing some very good speed ups. Versus, let's see, versus preconditioned Krylov. So anyway, that's a little bit of just sort of an eye candy chart. And then Axel Clavon and his colleagues have also have some research in Frosh, and this is sort of just showing some sort of classic test problems. You have a backward-facing step, lid-driven cavity flow, and then this is just a heterogeneous diffusion problem. And the takeaways here are that, compared to sort of some of the classic approaches like the pressure convection diffusion solution for a solver for the backward-facing flow, and then just their monolithic approach inside of Frosh is sort of very, very scalable, right? That in terms of number of iterations. And then for the lid-driven cavity flow, you can kind of see for increasing Reynolds numbers, you can see some very nice behavior for single level and then the 2 level. So I think that's what I want to say about that. All right, and so then the last thing that I want to mention is some work that's actually being done outside of Trilinos, but is using Trilinos. And this is work that Vin Dang and Joe Katulski have been doing in GEMMA. And so GEMMA is a frequency domain simulation code, uses a boundary element formulation. So the systems they come up with are these dense systems. They've developed this, what they call this multi-region distributed memory solver framework, where they can select different solvers for different regions. And the regions are these, as I understand it, are these exterior surfaces, these interior surfaces, and then there are slots or cracks, and there's...
Just like the image at the top.
Yes, just like the image at the top. Thank you. Right. And so, and they're essentially trying to characterize the electromagnetic fields in these cavities. And so the work that they've been doing depends on Cocos and Cocos kernels, and it does use Balos, the Krylos solvers inside of Balos. And so currently what they do is they use an additive Schwartz, and I should say that you have these sort of near field interactions and you have these far field interactions, and so they're using low rank approximations for these far field interactions. So you do not have a completely dense system. And so currently, they're using these additive Schwartz methods. An additive Schwartz method, just doing a local block diagonal preconditioner for the self-interaction blocks. But they have developed a new local preconditioner approach that they call simple algebraic approximation inverse, SAAI. And through some algebraic transformations, they can actually zero they can essentially make the preconditioner for the local block, and they can make it more diagonally dominant. And in an iterative process. And the impact is kind of given here in this chart, and it's actually pretty dramatic, right? You can go, if you look at the overall solve time, they go from, I think it's about a factor of 6 here, between the block diagonal preconditioner and then this SAAI preconditioner with 2 inner iterations. And so that's some really nice work. And they're, as I understand it, they're still exploring this on larger simulations. Okay. So anyway, that's all I have. And I just wanted to mention that there are upcoming talks, but people know that because you're giving the talks. All right. Happy to take any questions. Mm-hmm.
Sparse approximate inverse, whatever it is, AI. I'm curious, so I've had questions come to me. I know the original GEMMA Adelis solver does a lot of DIMs. Is it GEM? Is it doing GEMs in there, or?
That's a good question. I mean, the original Adelis solver was a direct solver, right? I think it was a sparse direct solver.
Three, right? There's the original, then there's the current. And so this question's coming up because the idea of floating point 64 possibly being emulated,
right,
and then GEM Ozaki schemes being really fast.
Right.
It could be that, like the SAAI one is good on our FP64 hardware, but if you actually get hardware that has Ozaki gems in it, then
right,
it could be that one of the prior preconditioners is a better choice. Because you're getting the gems out of it, right? You get more, I don't know.
Well, the problem with it was that it was never actually a scalable approach.
Okay.
Right.
Because, I mean, it was a direct solver, like on a fully dense matrix that was
Right.
treated as a fully dense matrix.
I mean, right. I mean, and it was a parallel direct dense solver. So I mean, that's pretty impressive, but it's a direct solver in the end, right? Yeah. So I mean, maybe the curve goes out further. Who knows, right? But
I had just a lot of random people at the vendor side asking me, kind of like our gym usage, how many
Yeah.
gyms do we do? D-gyms?
right. Yeah.
Because they know that can get optimized through the Ozaki 2 scheme with
Right.
emulated floating point 64.
Right.
And then everything else we have is not. And so they're looking for an exemplar where we could have kind of the good guy and a bad guy. And I was curious if Gemma was an example of that.
It's possible. I mean, I have to say I don't know all the details of this iterative process, but I believe that it does involve sort of locally dense systems. But
Yeah.
I mean,
They're still gonna be locally dense within the interior and exterior region of the.
okay.
It's gonna have a lot of, the other application I think would be good with usually reduced order modeling type of approaches to
Right.
generate dense matrices that are smaller. Any application that's leveraging something like that would probably have a high number of those.
Okay.
Just give them some GRS. Would that be enough? Give them some example problem with GRS.
That's right.
Yeah,
Ortho heavy.
well, there's sort of,
So.
Right.
But yeah, maybe we could talk about this more at some point. This is coming up in the kind of future planning on the GPUs.
Okay.
Where it's public that NVIDIA is using Ozaki 2 in
Mhm.
the future.
Right.
And AMD will have actual floating point 64 on their next gen that's public now. So
Okay.
there's questions if we can benefit from that Ozaki 2 stuff or not,
Right.
the emulated FP64.
Okay.
Because it is really fast. So.
Yeah. I would say probably Vin is the right guy to talk to.
yeah.
This is
Yeah.
just kicking off, so.
Sure. Sure.
Well, I mean, he's also looking at using, like, the next steps for this work, because I've been meeting with him, is looking at, like, recycling type approaches.
Uh-huh.
And those
Ah.
have the deflated subspace, right, they're gonna actually have more gems in them.
Okay.
Right.
Right, with recycling.
This is the outer iteration, or is this?
This is on the, yes.
Okay.
On the outer iteration, but, yeah, he's gonna
Yeah.
have subspace projection, which is meant to be a D-gem, so.
I'll
Okay.
talk with him about
Yeah.
it.
Okay.
It'll be fun.
Did you have a question?
Yeah, I got two questions.
Yep.
The first one is on the Laboratories equation that you showed earlier.
Yep.
Do you know which version of Trilinos was used to generate?
This?
Yes.
I don't. I do not know. I would.
Do you know how to find out?
If you scan the QR code,
Okay.
I'm going to read right now and see.
Okay.
Yeah.
Thank you.
Yeah.
And my other question is on slide 16, I believe, on
Slide 16. Oh.
the.
Yep.
I just want to make sure that I understand correctly what is on that slide, but do you think that this capability would be applicable to, let's say, a case where you have a solid domain and a fluid domain interacting, like where you can select different preconditioners or different?
I mean, as far as I know, this is strictly. I mean, this is very much tailored for this application. Yeah.
And the infrastructure itself is sitting in Gemma.
Yeah, I mean that's the other key is that this is sitting in this separate code, but I could get you the references. I do have the references. It's published in the open literature, and so if you were interested, I mean, you could either reach out to Vin or I could give you the references. Yeah. Yep. Okay.
Alrighty.
All right.
Jonathan?
All right. Thank you.